So today we're going to start doing some of the basics that you need to know before we can start tackling trigonometry. So it's going to take us a couple of days to go through some of these. For right now, we're going to start out with some of our basic geometry. And we'll start out with the most basic concept, most basic object in geometry, which is that right there. We talked about this a little bit last semester when we did areas and volumes. It's a location, geometrically called a point. And everything from geometry is built from that. You know, we talked about how a length or a line segment was created by just taking that point and pulling it in a single direction. That creates a line segment. And the length of that line segment was equal to the distance that we moved the point. Or we could take that point, grab it and pull it in a single direction and just kind of shoot it off into space forever. Keep going that way forever. That shape is called a ray. If we go back to the original point and we move it in a second direction and shoot it off into space forever, we get a second ray. What we have created in between them is called an angle. And that's what we're going to be studying in our trigonometry. And what we're going to be looking at today is different things and different ways of measuring angles so that we can study them in more depth. Now there's some things here. We have the sides of the angle. The rays, of course, make up the sides. And that common starting point is what we call the vertex. Now the measurement of the angle itself has kind of changed through the years. The original definition of the degrees of an angle, the measurement of an angle, was a difference in direction. Once upon a time, navigation was pretty popular, and a large segment of the population understood navigation. In navigation, the due east direction was the 0-degree direction. And you went around the compass counterclockwise. So north was considered 90 degrees. West was 180 degrees. South was 270 degrees. And then, of course, 360 degrees brought you back to 0, or east. And so if I had a point that started here, we always put the center of our little graph at the vertex of the angle. And let's say that I take off in this direction with a ray. And let's say that that ray, always measured from the angle from the 0 degrees, let's say that the direction of that ray is 19 degrees. So we have a second ray right here. And the direction of that second ray is 81 degrees. The angle between them is the difference in their directions. The difference between 81 and 19 is 62 degrees. So that defined the angle between those two rays, or defined the size of that angle, is that directional difference between the two rays that make up the sides. If we were to get it, and we won't get into a lot of vector addition in this class, but if you were to get into a lot of vector calculations and vector additions, this is still how this is treated for vectors, is by using these directions. Well, because navigation and the whole vector analysis isn't used near as much as it used to be anymore, we've kind of altered. There's a second definition of angles that's kind of come into play. Let's say we start out in a single direction and we start spinning around that end point there. If you spin around in one complete circle, that is how many degrees? 360 degrees. So one complete circle is 360 degrees. So from there we can go off of fractions of a complete circle. Let's say we start in this direction and we turn and we stop right here in the exact opposite direction. That is 180. Yeah, half of a turn, or half of 360 is 180 degrees. Or if we start in a single direction and we turn until it is, well, a square corner, or what we're going to define as a right angle, that would be 90 degrees. Now a 90-degree angle, a 90-degree corner like that, there's a little square in the corner, which signifies that it's a square corner, or 90-degree angle. Well, the 180 and the 90 here We just came up with those because they are certain fractions of the 360. We know this is half a 360. This is a quarter or 1/4 of 360. All of our other angles are defined in the same way. Of what fraction of a full turn are they? Let's say this here is 1/12 of a full turn, so it's defined to be 30 degrees. Or 1/15 of a full turn might be defined, whatever that comes out to be. So anyway, that's our measuring. The way the angles are measured, and we'll talk about this a little bit more tomorrow, is we just have a standard tool called a protractor. And tomorrow we're going to spend some time working with a protractor to measure angles. And we'll actually talk about, you guys might need to learn how to use a universal bevel protractor, which will take you down even smaller than a degree. But basically all we're doing is we're taking an angle and comparing it to something that already has known markings. It's a half circle that has the degrees marked out from 0 to 180. Of course, this is 90 up here. Somewhere in here is 40, 50. Yeah, it wouldn't hurt if you have your protractors, bring them in tomorrow, because we are going to be doing stuff. I have a few that I can pass out to use, but if you have your own, it would be cool. So then over here, this might be labeled the 130, the 140. But it's also labeled, if you look at it, 40, 50, like that. So how do we know which set of numbers to use? Well, when we look at angles, we have certain classifications of angles. We mentioned the right angle here. It has the square corner. If we have an angle that is smaller than a right angle, what is that called? Acute. Very good. I think of it this way. You think of small things as being cute. That's acute angle. It's small. Smaller than a right angle. If we have an angle that's bigger than a right angle, it's called obtuse. You might even, if you took a psychology class, you might talk about obtuse and acute thinking. Someone who is an acute thinker is able to focus in, a narrow angle of view. They can focus in on a problem and look at the problem and see all the tiny little details of it. The acute thinker, which is not a bad thing. An obtuse thinker is someone who can't concentrate on the details, but can get the wide view and see the big picture. So anyway, with those definitions of angles, if I come up here, and let's say my angle, I'm going to use a different color. There's a point down here actually where you always set the vertex of the angle on that little point. And then you line up one side with the bottom edge, or depending on how your protractor, there might be a line there. Set it up at the 0 or the 180. So let's say this angle sets up like this, and it goes like this. Is that going to be 50 or 130? 50. How do you know that's 50?
Because the right angle is 90.
You got it. This is an acute angle. If it's an acute angle, we have to read the smaller of the two numbers. The larger of the two is for an obtuse angle. So let's say I do have one that sits on here like this, like that. Is that going to be the 40 or 140? That's going to be the 140 because it's an obtuse angle. Okay. Now another way you can look at it is whatever side this tail goes on to, whichever one of the scales is marked 0, that's the one you read. The one that's marked 180, that's not the one you want. I always think it's a lot easier, it's acute or obtuse, whether it's a big angle or a small angle. We already talked about right angles. There's a concept similar to right angles. It's actually much more powerful, called perpendicular. Now, I draw a picture like this of two lines intersecting to form a right angle. And you might look at that and say, well, why don't you just say they intersect at a right angle? Well, in 2 dimensions, perpendicular and intersecting at a right angle or whatever are pretty much the same thing. But if we get into 3 dimensions, then there's a difference. I'm going to see if I can draw this to look somewhat 3-dimensional. Imagine that's a plane or a flat piece of paper laying on the ground, or laying flat. And we have a line that goes through that piece of paper. Perpendicular is stronger here. That means no matter what direction we measure the angle between that line and that piece of paper, it forms a right angle. No matter where we measure it, it is at a right angle in every possible direction. And that's what perpendicular stands for. So the perpendicular really takes on a much more powerful meaning in the 3 dimensions. Another thing that we're going to, and of course when we talk about trigonometry, we're talking about right angles or perpendicular objects is a huge, huge concept. Well, we could also have another special relationship. We could have 2 lines that look like this. They're called parallel. You guys constructed a set of parallels last semester, didn't you? Several sets? Okay. Definition of parallel. Well, most people say parallel lines never intersect, which is a perfect definition in 2 dimensions again. But if I'm working in 3 dimensions, here's 2 lines. Do they ever intersect? No, they'll never intersect. Are they parallel? No, they're not. They're just going in completely, totally unrelated directions. So the 3-dimensional definition of parallel, the technical definition is always equidistant. Or everywhere equidistant, however you want to say it. Equidistant means the same distance apart. Parallel lines will always be the same distance apart. We measure distance at perpendicular. So if I want to measure the distance between these 2 lines, I have to measure it perpendicular to them. That distance there will always be the same distance over here. Yes, sir?
But Todd, couldn't that be said for the same way that you just illustrated lines
Yep.
intersecting? Couldn't that be said for the same concept? I mean, they could be equal distance from each other and still never.
Yeah, but they're not equidistant everywhere.
Okay.
I can pick any point on any line, and from that point measure. I mean, if they're, like the whole thing like this or like that, there's a distance between them right here where they're the closest.
Right.
But if I pick a point here, I have to measure the distance to the other line somewhere.
Right.
Yeah. No matter what point I pick on either line, I'm going to measure it at a perpendicular to the other line, and it's always going to be the same distance, no matter where I'm at. That's a good question. And then, of course, we have lines look like this. In 2 dimensions, we just call them intersecting lines because they're going to intersect. In 3 dimensions, it could be what we showed you before, the lines that aren't parallel. That's what we call oblique lines. Oblique just means there is no special relationship between them. So let's start looking more at these angles. Obviously, we're going to be doing a lot of work with angles. Machining is one of the few applications where you need to really study down into things smaller than a degree. We've looked at a full circle being 360 degrees. So a degree is 1/360th of a full circle, which is pretty small. But for what you guys do, you're going to need to be measuring more precise than that. Just like feet can be broken down into inches and inches into sixteenths or whatever, hundredths or whatever you're breaking them down into. Degrees can be broken down into minutes. 1 degree is equal to 60 minutes. Which makes sense. 60 minutes in an hour, 60 minutes in a degree. That's easy enough to remember, right? 1 minute can then be broken down into smaller units. 1 minute is equal to 60 seconds. Exactly. So we still use that same terminology in machining. The symbols. Let's say we have something that is 3 degrees, 28 minutes, 39 seconds. We use that. So you got to be careful here. This is the same as the symbol for feet and inches. So you got to make sure you know what you're talking about. When we're talking, where it really gets confusing is if you have something written like this. That 18 feet, 40, in fact, 42 inches probably is the giveaway. Let's say I do it like this. Is that 18 feet, 9 inches? Well, to make sure you knew that that was degrees, minutes, seconds, we would put 0 degrees in front of it just to signify it. Now you know that that's an angle, not feet and inches. Now, some of the stuff we measure is going to be measured in decimal degrees rather than saying, whatever, 13 degrees, 48 minutes. you might just have 13.6 degrees. When you're doing your calculations, of course, your calculator is going to spit out decimal degrees. So one of our big tasks for today is we want to figure out how to convert between DD, which is the abbreviation for decimal degrees, into DMS notation, which is degrees, minutes, and seconds. So let's take a look first of how to start out with decimal degrees and go into DMS, and then we'll go the other direction.
Divide the point, whatever.
Close. You've got the right idea. Let's say we have 25.831 degrees. The part in front of the decimal point? Yeah, that is 25 degrees. We don't do anything with it. It's the 0.831 now that we're going to work with. That is degrees. We want it to be minutes. If you remember from last semester, our formal conversion, put it over 1, make it a fraction, put degrees down here, minutes up there. 1 degree is 60 minutes. So the degrees cancel out. The 1 times 1 is just 1. We don't have to worry about that. 0.831 times 60 is 49.86. Good. That's 49.86 minutes now, which means we're going to take the whole number off of that. That's 49 minutes. And now the 0.86 minutes is going to get converted into seconds. So this is over 1. 1 minute is 60 seconds. Minutes cancel out. 0.86 times 60 is 51.6 minutes. Depending on what textbook you're looking at or what you're dealing with, some places will tell you round to the nearest second. So 51.6 would become 52. Others will tell you you can have up to 1 decimal place in your seconds. So they'd leave it as 51.6. I don't really care either way. Really, it's up. You could ask Richard which way he prefers it. And if he prefers it one way or another, that's fine with me. Realistically, in the shop, we don't have any equipment, and most manufacturers around here don't have any equipment capable of manufacturing down to the second of a degree, of an angle. Realistically, the only ones I know of, the most precise ones I know around here, that go down to about 5 minutes is the most precise they get with their angles. So we will, for now, I'm going to put that up there as 51.6 minutes or seconds. Now I'm going to show you a little bit of a shortcut for this. We'll make this go a little quicker for you. Since I couldn't have done some of this calculation without a calculator. Let's show you how you would use your calculator and make this to go easier without having to type a whole bunch of stuff back in. So let's say we do a calculation. I'm just going to punch in something here to get an angle up there. So I get this angle right here, 56.54866.776. I'm going to keep this in my calculator so I don't have to round off. I mean, otherwise, if I were going to write this down and punch it back in the calculator, I'm not even going to go out to that 7 or 8 decimal places that are shown here. I'm probably going to only write down 3 or 4. I'm dealing with angles, especially if we're going DMS, always go at least 4 decimal places so that you don't have a huge round off error in your angle when you're done. But anyway, I'm not going to worry about rounding it off. The 56, of course, is my degrees. I'm writing down 56 degrees. All I have to do on the calculator now is go minus 56. I've taken it off. I'm down to my decimal. If I look at my conversions up here, my next step, I was going to multiply by 60. So I can just times 60. 32.92. Well, what part of that do I want? The 32 minutes. What am I going to do here? Well, first I got to subtract 32 to get rid of them. And yeah, then I am going to do times 60. 55.2. Not bad at all. Well, it gets even easier, and I'll show you in a second. Most of your calculators have a DMS function to them that we'll look at. I'll show you in just a second. Let's go now from degrees, minutes, second back into decimal degrees, and then we'll talk about your calculator function. Might have to have a little note sheet taped to the back of your calculator. Depending on the type, let's just look at your calculator. Anybody still have the old one-line display TI-30?
I have a TI-30 XS.
Okay, yours is good. You got a two-line display. Okay. Well, let's start looking at some angles in DMS notation and take it back to decimal degrees. So let's say we have 42 degrees, 49 minutes, 18 seconds. To convert this into decimal degrees, we just have to reverse the process. We start with the smallest unit and we convert it up. So I'm going to start with the seconds, and I have to convert those seconds into decimal minutes by dividing by 60. Yeah, 18 divided by 60 is 0.3. What am I going to do with that 0.3? I'm going to add it to the 49. Yeah, that's 0.3 minutes now. I'm going to add it to the 49. It's now 49.3 minutes. The 42 degrees, we're not going to worry about quite yet. Once again, that minutes has to be divided by 60 to make degrees. So 49.3 divided by 60 is 0.82 something. What's that? 8216, okay. 1667. Now what? Now we have to combine that with the 42 degrees. And there it is. Now I said go out at least 4 decimal places, so you could have rounded it off here as 0.8217 if you wanted to. Well, as before, let me show you an example of me doing this in the calculator without having to write so much down. So let's take 67 degrees, 28 minutes, 54 seconds. So in the calculator, I'll move this over so I can represent the calculator. I'm not going to punch the whole thing in this time. I'm going to punch it in piece by piece. I'm going to start with what? 54 minutes, or 54 seconds divided by 60. So that's 0.9 minutes now. What am I going to do with that? I'm going to add the 28 to it. And then divide by 60 to make that into degrees, and
Add 67.
add my 67. You got it. So 67.4817. Not so bad? I'm going to have you guys try a couple, and then we'll get back to looking at your calculators a bit. I want you to take 19.543 degrees, convert it into DMS, degrees, minutes, seconds. Once you're done with that, I want you to take 37 degrees, 15 minutes, 26 seconds, and convert that into decimal degrees for me. So we're going to pause right here and give you some time to do that. Okay, let's take a look here. So this first one, 19.543. So 19.543. Of course, the 19 degrees comes off. So I'll subtract the 19 off the calculator. Probably could have just not punched it in. 0.543, we're going to times 60. 32.54, which means we need 32 minutes. Subtract 32. And the 0.58 times 60 again. 34.8. So how many of you got 19 degrees, 32 minutes, 34.8 seconds? How many of you actually did it? Did you guys know what you did wrong? You got it? Okay. Let's go the other way. Right here, 37, 15, 26. I'm going to move that out of the way again. So I'm going to start out with the 26. What am I going to do? Divide by 60. And then add the minutes, the 15 minutes. Divide by 60. We have to make sure that we're being careful and hitting equals at each step rather than trying to string them together because it will mess you up bad. 0.2572, that's 37 then, 0.2572. How many of you got that? Cool. So let's look at how to use your calculator to cheat. Depending on your calculator, you will have a button that might say DMS DD like this. Otherwise, if you have some of the newer calculators, many of them have a button that looks like this. So the first step we have to do is figure out which button your calculator has. Or you might have a button that just says angle on it. Might say angle here or angle up above, one of the two. Is it on the button or above it?
It's above it.
It's above it, so you're going to have to do a second or a shift depending on your... So let's say that you are going to enter, let's go back up here. Let's say that we are going to turn this one from decimal degrees and degrees, minutes, and seconds. You would just enter 19.543. Hit whichever one of these two buttons you have. And then you use the arrow to get over to where it'll say 2 DMS or a little arrow DMS.
So DMS, it says DMS 1 degrees, and then below it says 2. I'm guessing that's minutes, and then 3 seconds.
Okay, let me come take a look. You're going to that same menu, and you're going to type in 37. Then you're going to go to that menu and select the degree.
You take the 37 in first.
Type in the 37, go into that angle menu or the math menu, depending on your calculator, and select the degree.
Okay, so
Then you're going to type in 15 and go to that menu and select the second symbol. And then you're going to go type in the 26 and go in that menu and select the minute symbol. The exception to this would be if you have a graphing calculator. I don't think anybody's using a graphing calculator today. If you end up using one, let me know and I'll show you how to do it on there. It's just a little bit different. And once you do that, once you've got that entered, just hit equals, and it should automatically change it to decimal degrees for you once you hit equals.
okay, so once you have it punched in,
Yep.
hit enter.
Automatically. Good. Okay, well, I'm cutting into your homework time right now, so I'm going to cut it off here. I had intended to do operations with angles and degrees, minutes, and seconds. What I'm going to do is I'm going to include it in your homework, but we'll talk about it more tomorrow. The operations are just like our operations we had with feet and inches and pounds and ounces. So let's just see if you guys can handle it on your own without seeing me do some examples. Otherwise, we'll do some tomorrow in class. So in the packet I handed out, it is page 266. Hold on to your seats. This is going to get ugly. 1 through 75, the odds.
1 through 75?
Yeah, you had nothing better to do tonight, right?
I got it. Swimming to chase time.
Well, you're better off doing